Hey all, in this video we're going to look at complex numbers, and we'll start with the definition of what they are, work through how to do the four operations: add, subtract, multiply, and divide with complex numbers, and then at the end we'll look at simplifying radicals using complex numbers. So a complex number is a number involving, well actually let me start with the definition of the imaginary number I. I is defined as the square root of -1. And so in earlier algebra classes, if we ran into a negative under a radical, we would just say D and E does not exist. And it doesn't in the real numbers, but it does exist in the imaginary or complex numbers. So this is kind of the next level up in terms of how solutions can come out. So by definition, we let I stand in for the square root of -1. It's the same idea as if we have pi, which is that 3.14 blah 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 number. Instead of writing out that whole number every time, we give it a symbol to abbreviate it to represent this number that doesn't repeat and doesn't end. So with this, it is much easier to use i's in things than to write square root -1s everywhere. So this is just a convention to make it easier to work with. And then by definition, I squared will be -1, and we'll see where that pops up here in a little bit. For standard form for a complex number is where we have a real part, which is a, plus an imaginary part, which is the bi. And so a plus bi is the form that these numbers are going to take. We see them show up in solutions to quadratics later in this chapter, and they pop up in lots of places. Electrical engineering in particular, I remember when I was in school, we used complex numbers a lot. Okay, so let's see how we can add, subtract, multiply, and divide with them. For most of the four functions, they would behave pretty much exactly as you would expect. If you sort of treat these as like terms, the a and the bi, that is what they would do. So I have these two complex numbers adding. Let me get rid of the parentheses and just rewrite it. I'm going to write that as -5, because since it's a plus, these signs wouldn't change. And 2i. And kind of exactly what you would think you would do is go 4 minus 5 and put the real parts together and get a -1, and then put the complex parts together, -7 minus 2, that would make -9i. And that's simplified. We're in standard form, a plus bi, where a is -1 and the b is -9. That's as far as we can go. So adding, subtracting, not too bad. It works pretty much the same as it does with polynomials, as will multiplying largely. So for this one's a minus. So when I rewrite this out without the parentheses, I have to be careful to get that sign distributed, just like usual when we're looking at a problem with parentheses. So minus and minus would make that a +7i. And again, we just collect our real part and our imaginary parts together, and that would be it. So -10 for the -4, -6, and 2i plus 7i would give 9i. And that's it. For these next two, we are a couple of versions of multiplying. This, we would multiply the coefficients and then multiply the i's. They work a lot like they would if they were x's. So -6 times 2 would be -12, and I times I would be I squared. And if you remember up above, I squared is defined as -1 in this box up here, right there. So that means this I squared can be simplified a little bit to a -1. And then -12 times -1 will make +12. This looks like a distribute, which is exactly what it is. 3i times 4 would give us 12i. 3i times -5i would be -15i squared. And again, anytime we see the I squared, we have to simplify that. So that would be -15 times -1, which would change that to +15. And while that's simplified, it's not quite an a plus bi form, so I'm going to rewrite that with the a first and the bi second. And then that would be as far as we could go. These next couple of multiplications are, this looks a lot like a FOIL, which is exactly what you would do. So it's nice the complex numbers are not very hard to work with, as they're fairly intuitive, at least at these basic versions. So if we start foiling, we're going to go 1 times 5 and get 5, 1 times 2i and get 2i. On the inside, minus 3i times 5 is minus, minus 2, I'm not sure where that 2 is going. Minus 3 times 5 would be minus 15i, and then on the end, minus 3 times 2 would be 6, and I times I would be I squared. So we got a little bit of simplifying to do because we're not in a plus bi form, so that's how I know I'm not done yet. So we'll go 5 out front, 2 minus 15, since these are like terms. That'll make a minus 13i there. And then remember, I squared is negative 1, so this is going to be a minus 6, because that 6 times negative 1 would flip the sign. And then a couple more like terms, 5 minus 6, so that would be negative 1 minus 13i. Oh, you know what? I just noticed I have a sign error right there. There's a minus 3 times a plus 2, so that should have been a minus. And then I squared, that would be negative 1 times negative 6, and that should be a plus 6 right there. Okay, so then 5 and 6 makes 11, and then minus 13i. For this next one, this is going to be, so remember when we have something squared like this, we can't distribute the squared. What that really means is I have 2 factors of 7 plus 2i. So it's really a lot like this problem. So I'll just rewrite those side by side. If you happen to be really good at special products, you can do this out in your head. I think most people are not that good at special products, like we saw in the factoring section. And so instead, I would probably just suggest you FOIL it out. So 7 times 7 is going to be 49. 7 times 2i is going to be 14i. So 2 times 7i would be 14i again. That's that 2ab in the middle of the formula. And then 2i times 2i would be 4i squared. So kind of the same things as here. We have a little bit of simplifying that we can do. So 49, 14, and 14 would be 28. And then plus 4 times I squared, but I squared is negative 1, so that's going to change that to a minus 4. And finish collecting alike terms. And then there we have our answer in a plus bi form. These next ones, this is also reminiscent of the special products. When we were looking at factoring, when we had a plus b times a minus b, that came out a squared minus b squared, and it was our difference of squares. For when they're complex conjugates, the b has that I attached, so because it would be a squared, if I FOIL it out, I would have a squared, and it'd be minus b squared I squared, because the cross terms would cancel. But remember, I squared is negative 1, so that's why in the formula it flips to a plus right there. So for these next ones, when we happen to be multiplying conjugates, which we'll do for division here in a second, you can just do out the steps. So let me show that, and then I'll show the shortcut using the formula as well. So 5 times 5 would be 25. On the outside, we're going to get a minus 15i. On the inside, we're going to get a plus 15i. And then on those last terms, we're going to get a minus 9i squared. Those cancel. So then I have 25 minus 9 times negative 1, because I squared is negative 1, which gets us 25 plus 9, or 34. So the shortcut version of this, the shortcut version is just to say a squared plus b squared, which was pretty much right here. A is 5, so 5 squared plus b squared. B is the 3, not the I, just the 3 itself. And there's your 25 and 9, makes 34. So you can kind of skip all that, the FOIL on these, and then just use your complex conjugate formula. This one, again, let me kind of show the steps with the FOIL, and then I'll show the shortcut at the end. This one's slightly trickier because of the invisible 1 in front of the I. So 14 times 14 would be 16. I'm saying 14. 4 times 4 would be 16. 4 times I would be 4I. And then negative 4I. And then on the end I'll have minus I squared. So those cancel. I get 16 minus I squared, that'd be minus negative 1, so that's plus 1, and it equals 17. So when I do the shortcut on this, it would be 4 squared plus 1 squared. A lot of times people will put I squared there instead, which then flips it and makes it a minus, which it shouldn't be. The 4 minus I, the B on that is actually the invisible 1 in front of the I, so we're saying 4 squared plus 1 squared. Place where we use complex conjugates is for dividing, and so this is kind of the basic form of one of these, where we're going to have some sort of complex number in the denominator, and if we have a plus bi in the denominator, what we do is we multiply by its conjugate, a minus bi, or the reverse sign. So if this is a minus, this is a minus. I can only multiply things by 1, expressions by 1, so that they maintain the same value. So we're going to do a minus bi over a minus bi, or pluses if this had been a minus. And what that does is it cleans up the denominator to something that's going to be, like, notice both of these came out to 34 or 17. They came out to numbers not involving I, and that's what we're trying to do when we're dividing these, is to get it in a plus bi form and get the I up out of the denominator. So for here, there's a couple of things I could do, but let's kind of stick to that plan. With this one, it's a little harder to see because there is no a term. The a term is 0. So if I wanted to write this in kind of strict a plus bi form, it's 0 plus 5i would be this denominator. So its conjugate would be 0 minus 5i. So when I go to multiply this one, I'm not going to use those zeros, but what I'll do is I'll multiply it by negative 5i, negative 5i. So with that, the top would be a distribute, so it's like this, and the negative 5i is multiplying both of those. And I think I could probably just actually use negative I, but just to kind of hold with what this says, I think I'm going to do it out the slightly longer way. It also lets me show a little bit of reducing that I'd like to show anyhow. So I was debating which way to do that, so I'm going to do it the slightly longer way. Negative 5i times negative 20 would be 100i. Negative 5i times 30i would be, that would be minus 150 I squared, and then 5 times negative 5, that's going to be negative 25, and then I times I would be I squared. Cleaning all that up a little bit, I'll sneak up here with it. This would be 100i, and then that I squared is going to flip that to a plus. And then, again, I squared is going to flip that to a plus. And right now, this is written a little backwards because I have my term I leading, so it's bi plus a. So let me rewrite that in the right direction. 150 plus 100i. And then the 25 belongs to both of these, so I'll write it as two separate fractions just to make the reducing a little bit easier to see. So 150 over 25, that would end up being 6, plus 100 divided by 25 would be 4i. And so you can see I got the I out of the denominator, and now I'm just in a plus bi form. Again, I could have skipped the negative 5 on that. I kind of wanted to show it in terms of the complex conjugate, why that's what we would use. If I had, I would have had a little less reducing to do. This would have been only 5s down here, so these would have been 20s and 30s still that I would have reduced and gotten to the same spot. But doing it that way makes a nice intro to this one, which was kind of my plan. So here, I have a 4 plus 3i showing in that denominator, which means I need to multiply it by 4 minus 3i, because that's going to be my conjugate. So in the numerator, we're going to have minus 3i times 4, so that's minus 12i. Minus and minus is going to be plus, and then that will be 9i squared. Downstairs, this is where I would encourage you to use the shortcut. It's going to be 4 squared plus 3 squared. And there really isn't any reason to make that any harder. You could do out the FOIL, and like I did in that last example, you're eventually going to land here, but I would just go directly to there. Let's get things simplified a little bit. So this is going to be a negative 1. So negative 1 times 9 would make a negative 9. I'm also going to flip the order so that I'm a plus bi form again. So negative 9 coming out front, minus 12i going to the back, and then that is over 16, and 9 would be 25. And in terms of reducing these, if you have, this one doesn't reduce because the 25 doesn't work with either the 12 or the 9. If you have an answer where one reduces but one doesn't, so let me just make something up here. Let's say I had 5 plus 7i over 10. I could simplify the 5 and the 10, but the 7 and the 10 doesn't simplify. So under those circumstances, at least in the computer, they usually just leave this thing written in that form over the common denominator. If both reduced, so say I had, instead of that, say this was a 15, then there's a 5 that could be reduced out of all those places. So 5 would go into 5 once, 5 would go into 15 3 times, 5 would go into 10 twice. So if it reduces in all 3 places, then we would need to reduce that. But if it's only one of the 2 fractions, then we usually just leave it as it is. And then this last division problem, same thing. This one has a negative out front. It doesn't actually change anything, but I just wanted to do an example showing it doesn't change anything. So we would use negative 1 minus 2i and negative 1 minus 2i. So notice we are not changing the sign on the first term, and we didn't on any of those previous problems either. Whatever that first one is the same, and the conjugate is the opposite with the I term. From there, we're going to FOIL the numerator, and the denominator will use the shortcut. So 7 times negative 1 for negative 7, 7 times negative 2 for negative 14i, I times negative 1, so that's negative I, and I times negative 2i would be minus 2i squared. And then to avoid doing all that again, we'll just do negative 1 squared plus 2 squared. Negative 7, just bring that over, minus 14 minus 1 would be minus 15i. And then that is a negative 1, so negative 1 times negative 2 would flip that to a 2. Negative 1 times negative 1 is 1, plus 2 times 2 would be 4. And then collecting our terms, we got negative 7 plus 2, and so that is negative 5 minus 15i over 5. And so this is one where I do have to reduce, and the denominator goes in evenly to both. So 5 goes into 5 once, so that would reduce down to a negative 1. You can think of this, I think I did this with the 1-2 problems ago. You can think of this as 2 totally separate fractions, if that helps you see how to reduce. And then 5 goes into 15, that would be minus 3i. So that would be our final there. Where we're going to see these complex numbers come from is, if you happen to remember the quadratic formula, when we get a negative under the radical in the quadratic formula, that's where we're going to have complex solutions or imaginary solutions. So this is just a little bit on how to simplify roots with negatives under the radicals. It follows all the same principles as simplifying roots without negatives, except for the multiplication rule, which is if I have root A times root B, this one only works when A and B are positive values, and you'll always see that little rule added to this multiplication rule, or condition added to the multiplication rule. Generally what we want to do if we're going to do math with any of these things is rewrite the root in terms of I first, and then do whatever math is still required. And so generally, if I have square root of a negative value, I can just rewrite that instead of writing it as square root of -1 times the value b. We just use the I there to indicate that it had been a negative. So for this, square root of 25, -25 would be, square root of 25 would just be 5, right? And then with that negative, that means it's 5i. And that's kind of that's the difference, is when we see the negative, we're going to get the I indicating the negative. So here we'd have -3, and then that's going to be times the result of the square root of -100. -100 under a radical would be 10i, and -3 times 10 makes -30i. For square root of -20, remember that 20 is 4 times 5. And when we can reduce when we simplify part of the radical, so in this case it factors to a perfect square and another number, we need to bring that 4 out front as a 2. And that's the same thing we're going to do here, so 2i root 5. That's the way that I learned to write them, so that you could tell that the I wasn't under the radical. I think some people also write it 2 root 5i. These mean the exact same thing. They're identical to each other, but sometimes you'll see it written this way, sometimes you'll see it written that way. I guess the advantage to this is if you're thinking like a plus bi form, then it's maybe a little more clear that b is 2 root 5. This version I like, because like if we had an x, we would put it there so that you could tell it wasn't under the radical. So sort of for that same handwriting reason, I prefer this one, but I think you may see that one on the homework, at least on a couple of the questions. And then square root of -19. 19 doesn't simplify at all, so this would just be I root 19, or again, if someone's writing it in strict bi form, they might write square root 19i. I prefer this one, but again, some people prefer that. And then for these last 3 examples, this is going to be -5, and then the square root of -100, we just saw that one actually, that would be plus 10i. And then I can't take that any farther because that's an a plus bi form, so that would be it there. Here, square root of 49, -49 would be a 7i, and then minus square root of -121. 121 would be 11, and then the negative makes it I. So then in this case, there's a couple of like terms there left to collect. So 7 minus 11, and we get minus 4i. This is the form that we're going to see quadratic formulas. When we do the quadratic formula, we'll often get an answer in kind of the shape. It's the -b plus or minus all the stuff from the radical over 2a. And so this one's just kind of meant to help get ready for simplifying those. So the first thing we can do here is simplify that radical. So 72 is 36 times 2. So 36 is the biggest square that divides into 72. So when I go to simplify just that much of it, I would have 8 plus a 6 would come out, an I would come out, and root 2 is left behind. And then that's all over 6. For me, I'll write this out kind of the long ways, and I'll show you how I do this a little bit quicker when I'm just doing it for myself. What we want to do is look at all 3 terms and see if there's anything that divides into all 3 of them. So in this case, 2 divides into 8, 2 divides into that 6, and 2 divides into that 6. So I wouldn't suggest writing this. I did in the notes just so that people could kind of see what I was canceling. But if you look, there's all these 2's everywhere, so 2 over 2, and the denominator belongs to both terms. So all of those 2's cancel out, and we're left with 4 plus 3i root 2 over 3. When I'm doing this for just myself, so I'm looking here, here, and here. Those are the 3 places. The number isn't going to divide into the root, which is okay as long as it divides in the coefficient. If you think about if we had 8 root 2 over 4, I can reduce that fraction. It doesn't have to go into the 2 as well. It would just go with the coefficient. So here I just think, okay, 2 goes into 8 4 times. It's not a very good 4. 2 goes into 6 3 times. And 2 goes into 6 3 times. And then I have 4 plus 3i root 2 over 3. So to me, that's kind of the shortcut that I'm doing in my head. That's really, I can do that because I'm canceling these 2's from everywhere. And we'll see more of that when we do quadratic formula. It's fairly common for them to reduce like that.